Hello, and welcome back to our series on Vertex Operator Algebras. Today's a quick episode where we'll construct two particularly useful Heisenberg modules out of those affine Lie algebras we discussed previously. So let's start with a quick review of affine Lie algebras, which are the subjects of lectures 12 and 13. Let H be a Lie algebra equipped with an inner product. Recall that the affine Lie algebra associated to H is the central extension of H's product with the algebra of Laurent polynomials in some formal variable t. The Lie bracket associated with the structure is as you'd expect, but also includes a central term proportional to the inner product of the two elements from H. Moreover, that central term has homogeneous degree 0 with respect to the natural z grading from the algebra of Laurent polynomials. We call this resultant Lie algebra H hat. You might also recall that we can twist H hat by taking those elements of a half-integral graded H hat that are invariant under the action of some isometry, in particular, in this case, an involution. As you may recall, these amount to the even-even, odd-odd, and central subspaces of H hat under that involution. The resulting twisted affine Lie algebra is defined with respect to that involution. Let's call it theta. Now for today's construction. Suppose that H, the underlying Lie algebra, is abelian. We claim that the commutator subalgebra of H hat is a Heisenberg algebra. Proof. H is abelian, and the center of H hat, which doesn't vanish, is precisely the central terms from the Lie bracket, i.e. those proportional to the inner products from H, and the central charge, which, as we have seen already, have homogeneous degree 0 in terms of the Laurent polynomial z grading, which is basically the extension f of c. Thus, the commutator subalgebra of H hat satisfies the requirements for a Heisenberg algebra, as was to be shown. We can repeat this construction for a twisted affine Lie algebra, and to that end, let's consider the involution on H that acts by multiplying elements of H by -1. In this case, the Z2 grading induced by this involution has a trivial even subalgebra. Put differently, H is entirely odd under theta equals -1. So H hat of -1 is entirely comprised of a central term and the odd-odd involution subspace, meaning it's proportional to half-odd integral powers of the formal variable t. Following the exact same arguments for H hat, we find another Heisenberg algebra, the commutator subalgebra of H hat of -1. Let's make the notation here a bit more uniform and refer to the untwisted case as H hat sub z and the twisted case as H hat sub z plus 1/2. So again, H hat sub z has a natural z grading, and H hat sub z plus 1/2 has a natural half-odd integral grading, or if you like, a z grading that's shifted by 1/2. Both of these Heisenberg algebras have representations in terms of m of k, which are isomorphic, of course, to the symmetric algebra of their respective even abelian subspaces. In both instances, the central basis element, often called z or z, is represented by the central charge, c. So c acts on m of k by multiplication by k. Actually, following FLM and in what follows, we're going to fix k equal to 1. And as we shall see later, this is a deliberate choice that will have an important consequence later on. But for now, it allows us to simply treat the action of C as the action of the identity map. And that's all for today. Next time, we're going to do a little bit more work on inner products and involutions.